Have you ever really thought about what's going on in your brain when you're asleep? Well, for decades, trying to analyze those signals has been a massive challenge. But today, we are diving into a totally new AI framework that's designed to decode our sleep with honestly stunning accuracy. So first, let's just set the stage here. You got to imagine this. To diagnose a sleep disorder, a highly trained expert has to sit down and visually comb through hours of brainwave data, classifying every single 30-second chunk by hand. It is incredibly time-consuming, it's expensive, and, it's just ripe for human error. This has been the major bottleneck in sleep science for years. And this all leads us to what the experts call the sleep staging problem. So, what is sleep staging? Well, simply put, it's the science of labeling these little 30-second windows of sleep, they're called epochs, into the right category. Is the person awake? Are they in light sleep, deep sleep, maybe REM sleep? Getting this right is absolutely crucial for understanding a person's sleep health. So, what's the one key insight that makes automating this even possible? It's this. Sleep isn't just a random jumble of states. It's a process, right? It flows. And the research shows that a whopping 83.3% of the time, one epoch is the exact same stage as the one right next to it. That dependency, that's the secret sauce that these AI models are trying to figure out. So how did we used to try and automate this? Let's take a quick look at the older approaches. And to make this really easy to understand, we're going to use a simple analogy. Think of each 30-second sleep epoch as just a single word. And a whole night of sleep? Well, that's the complete sentence. Okay, so the most basic AI method was called one-to-one. The AI would just look at one epoch, so our word happy, and it would make a decision based only on that. It kind of works, but it completely ignores that crucial dependency we just talked about. There's zero context. So of course, the next logical step was the many-to-one method. Now the AI looks at a whole sequence of epochs, like the phrase, a very happy day, to figure out the one in the middle. This is better. It uses context, but it brings up a really subtle and serious problem. How do we know the AI is actually learning from our target word, happy, and not just getting confused by its neighbors, very and day? And in fact, the researchers themselves call this out. They call it modeling ambiguity. They say, quote, it remains unclear whether the network is truly modeling the class distribution of the target epoch. Basically, the AI might be learning the wrong thing, which is going to lead to less reliable results. So to sum it up, this older kind of common sense approach had two huge drawbacks. First, that modeling ambiguity we just mentioned. The AI gets confused. And second, it's just slow. Forcing the AI to process 3 times the data for every single decision is really, really computationally expensive. Which brings us to the breakthrough. A totally new way of thinking about this whole problem, the one-to-many method. Let's go right back to our analogy. The one-to-many method is, well, it's genius. The AI looks at only one epoch, just our word happy. And from that single piece of info, it not only classifies happy, but it also predicts its neighbors. This forces the model to develop a much, much deeper understanding of the hidden patterns in our sleep. The formal name for this whole technique is joint classification and prediction. Essentially, the model is doing 2 jobs at once. It's classifying the present moment while also predicting the immediate past and the immediate future, all from a single input. So, how does this actually make the result better? Well, it's all about creating what's called an ensemble of decisions. For any single epoch, we don't just get one opinion, we get 3. We get the main classification from that epoch itself, we get a prediction from the epoch that came right before it, and a prediction from the epoch that comes right after it. By combining these 3 votes, we get a final decision that's way more robust and accurate. It's kind of like having a small committee vote on every single 30-second slice of sleep. Okay, so that's the theory. It sounds great on paper. But what about the results? How well does this new method actually perform in the real world? The headline number is 83.6% accuracy. And look, this wasn't on some small, cherry-picked data set. No, this was achieved on the massive MASS dataset, which has data from 200 different people. That is a truly state-of-the-art result. And when you put these methods head-to-head, the results are just crystal clear. The simple one-to-one method on the left, that's our baseline. Then in the middle, you've got the many-to-one method, which you can see it actually does a little bit worse, probably because of that modeling ambiguity we talked about. And then over on the right, the new one-to-many framework is the undisputed winner. So let's just recap the whole thing. The old many-to-one method was ambiguous and it was expensive to run. The new one-to-many solution is precise because it only focuses on a single input, and it's incredibly efficient. But just how efficient are we talking? This is honestly staggering. Just look at the training times. The old many-to-one method took about 4 hours to train on this dataset. The new, more accurate one-to-many method, only 1.6 hours. It is almost as fast as the simplest possible model. So it's not just better, it's way smarter and more efficient. Okay, so the tech is clearly very impressive, but what does this all mean for doctors, for patients, and really for the future of medicine? Well, the implications are huge. This means we can get faster, cheaper, and more accessible diagnoses for sleep disorders like sleep apnea. It really opens the door for the dream of reliable at-home sleep monitoring to become a reality. But even bigger than that, it proves out a powerful new way for AI to understand any kind of complex sequential biological signal. And that's really the thought I want to leave you with today. We've seen how this incredible method decoded the language of sleep. But what's next? What happens when we apply the same powerful predictive framework to understanding heart rhythms or detecting seizures, or maybe even the complex brain activity of our waking lives? The possibilities are just absolutely fascinating to think about.